Generics are a very powerful component in Python's type system, but not many people know how to use them. In short, they allow you to create generic classes where you can use a specific type structure as a template and then specify more detailed types in specific situations. And this allows you to have one interface that supports multiple types. You can also get really clever with it and actually create a class that is able to introspect its own type based on the variables you pass to it. So in this video, we're going to be learning what generics are, and we're also going to be covering a simple use case as well as a more complex real-world example. Of course, if you find the video helpful at any point, then consider leaving a like to let me know, and maybe subscribe if you want to see more videos like this. But with all that out of the way, let's take a look at the power of generics. To try and explain generics as best I can, I'm going to go through two examples. The first of which is a much more illustrative example than an actual useful example. And the second is a much more useful example, but also quite an extreme example to really show the power of how you can use these things. But first, I want to do a quick primer on TypeVars because they are going to be necessary to understand what's going on. So if we create a typevars.py, yeah, that's fine. And then we could do from typing import typevar and then t equals typevar t. And what this means is that this can be any type, but it's quite special in the fact that it inherits, quote unquote, types from other places in the signature. So it's sort of a dynamic type in a way that is used to do static typing, which is an interesting way of doing it. But the easiest way of showing this off is to create an echo function, which takes a variable of, we're actually going to use value of type t, and then it just returns the same type. Because it just returns itself, it will take a value of type t, and then it will return a type, it will return a value of type t because it's just returning itself. And now if I were to say x equals echo 2 and y equals echo string, so the type system is able to work out that this number 2 here is an integer and this string is a string. If we hover over x, we can see that x is considered an integer and y is considered a string because it can see what type is being passed in from here, and we're saying, okay, that must be type t. So when we call this, t becomes an int. When we call this, t becomes a string. We then expect to return the same type out. So this also becomes an int or a string, and we realize, okay, we are returning an int or we're returning a string. And that's the simplest example to show off what typevars do. You can also, if you really wanted to, bind them to something. So if we were to say bound equals int, then this will complain because the value that we pass in to echo must be a subclass of int. So we can pass another int in here. Weirdly, we can pass a ball in here and that'll be fine because balls are subclasses of ints. That's not strictly necessary to know for generics, but it's probably very helpful to know if you're doing some more advanced stuff. So if you move on to our illustrative example, and we're going to call this fruitbox.py, and then we're going to do from data classes import data class. We're just doing that to save time. And we're doing from typing import generic and typevar. And then we set t, which is a typevar of type t. And then we're going to have some items that go in a box. So the example we're going to do is we're going to have a box which is a generic type, and then we're going to be able to put items in it, and it will be able to say using the generic type system which type we want to put in it. So we can do a data class, and we can do class apple, and we'll just give it a name which is a string of apple, and then a data class of we'll use banana because that's my favorite fruit. And then we'll have a class called box, and this is going to inherit from generic t. So this is the quote unquote old way to do it. It's also, as far as I'm aware, the latest, also as far as I'm aware, MyPy only supports Python 3.12 generic types in the latest version, which is unreleased at present. If you were to do it using the new system, you could do box T like that. Actually, we might see, are we going to get away with that? No, we're not. See, PEP 695 generics are not yet supported, but that's how you do it using PEP 695. I will leave a GitHub link in the description with the old way of doing it, and then other files with the new way of doing it as well, so you can compare the two. And if we were to say create an init and then have self and then return none, and then we do self.items equals an empty list, and this is going to be a list of type T, and then we can define add self.item T, and then we can define def remove. There we go. So now we can add and remove items to the box, and notably the item will always be of type T. Now of course we don't actually know what type this is yet, but we could say if we do if name equals main, there we go, that box is a box of type apple, and then we can instantiate it like that. And what this is now saying is that we want our box to only contain apples. So now apple will be T, or T will become apple in this case. So by process of elimination, we could say that self.items is a list of apples. When we want to add an item, we want to add an apple, and then we remove an item, we want to remove an apple. So we could do, let's call this apple box, and then apple box dot add. I cannot type today. Apple. There we go. And the type system is perfectly fine with that because we're adding an apple. If we were to have a go and add a banana to the box, the type system would complain because argument 1 to add a box as an incompatible type banana expected apple. If we were to change this here, we would see that it would now complain about an apple being added to the box. And this is because the generics allow you to specify the type as you create the class to be able to create more generic and therefore dynamic types. So if we set this back to apple and we go for another example, we can set banana box equals banana box, which we need to define. So if we define banana box as box banana here, and we could just pass this because we're inheriting from box, but notably, we are setting the generic type within our inheritance. So we're now saying that instances of banana box will always be a box and T will always be banana. So it will always contain bananas. And then we don't have to define it down here. And if we were to do banana box to add banana, it would have worked fine. If we were to do banana box dot add apple, it would complain because it expected a banana. So those are the basics in how generics work. They allow you to create more generic classes in that they can work with any type. But this does, unless you subclass the generic type, force you to actually specify the type down here, which is fine sometimes, but it is a little bit annoying if you don't necessarily have to do it. There are ways to create a generic type that will be able to automatically infer the type that it should use based on the way it was constructed. And that is what I'm about to show you next. Before we move on to the next example, I just want to say that it is quite an advanced example. It is probably one of the more advanced uses for generics you'd come across. I wanted to talk about it, one, because it was the example I had in real life, and I like to put real life examples in these videos. And two, because I wanted to show the sheer power of generics and how you can use them to do crazy things. But I just wanted to jump in and say, if you don't fully understand it, then honestly, don't worry about it. So to save on a bit of time, I have created our generic class already. So a bit of a run through about what this does. This is very similar to the example I showed in the descriptors video, except it's not a descriptor. Don't worry. I haven't done all that in it. But it's a generic class called envar. And basically this value down here, when you create an instance and then call the value, it will get an environment variable of self.name, or if it can't find it, it will use self.default if provided. if a converter has been supplied, then we can return the type of t, and then we can return the converted value. So this will allow you to convert, because environment variables, keys and values must be strings. This is a mechanism that allows you to convert them to ints or bools or something like that. Or and if there isn't a converter, we just return the value. And then we take self.name, self.default, and self.converter as variables. The converter is a callable that takes a string or none and returns type C. So this will be the type that we want to convert to. And that will be, you'll see how that's used in a little bit. Down here, we also have a function that can convert it to an int, and then we pass that in here. And if we were to look at value right now, we would see that Python doesn't know what the type is. It knows that it will be a type based on envar, but it doesn't have enough information to be able to infer the type. If you were to give it a type like int, then value would be recognized as int, because we've already set up everything. So we return type t, we pass type t in here. If we set this to be an integer, this will return an integer. But there is a way to make it understand that by introspecting the function's signature, and that is by using overloads. So if you've never used an overload before, you could specify multiple possible function signatures for a specific function using overloads, and then you can have a master function of sorts, which will be this, that actually implements what we want to do. So to do that, we can do overload, and you can use them on methods, and you can, crucially, in our case, use them on class init methods. So there are 3 overloads that we want to do. So we want to do an overload of def init self, and a name, which is a string, and then that will return none. And then we don't need to implement anything, so we can just use ... And then we also want to do an overload def init self name string, a default, which will also be a string, or none. And we'll just leave it at those 2 for now. Between these 2 function signatures, we have this default mechanism down, because in this function signature, default will be none. In this function signature, it'd be string. So we have all this here. If we were to look at this now, oh, sorry, I haven't actually done everything we needed to do. There's one more thing we need to do, and that's actually to type hint the self parameter, which is not something you would typically do. But if we were to say set env_var as string or none here, and say env_var string here, what we're saying is that if a default isn't provided, then the name may or may not be an environment variable, and as such, this the env will be string or none. If we do provide a default, there's no way that we can return none out of value, because if the string isn't there, we'll use the default, which is a string. So we can say that self is envar of type string. And now if we look down here, we can see that this without a default is registered as string or none, and this with a default is registered as string, because it will always be a string in that situation. As far as the converter goes, we can go even further and specify a 3rd overload. So we want to do overload def dunder init self. We'll leave that alone for now. Name string, default is string or none in this instance, because we don't care what the default value is. And then we can specify a converter, which will be a callable of string or none, and it will return C. And then the callable is optional, so we can say or none, and then by default it's none. And now we've satisfied everything down here as well. And that matches up with this function signature here. So we have a callable that takes string or none, and in this case, C is int. So that follows on from our TypeVar example, where we pass int in here, and T gets set here. We provide int as a return type here, and that gets set as C here. And you can actually set env_var to use the generic type of C. and then it will complain because I've put it on the wrong one. That was good. I meant to put it up on the overload. So you wouldn't need to put it down here, but you would want to put it on the overload. And now this function returns int. So you can see we take a string on it, it returns int, and value is an int. If we were to change this to bool, which works out the box, weirdly int doesn't. I spent such a long time, I think it was last night or the night before, trying to make that work, and I just couldn't. So if anyone does know how to make that work, do let me know. But if we set this as bool, then we can see the value is now a bool. And we can now provide a converter to our environment variable, and the static type system will know what the type will end up being, because whatever we do with this converter, it will always be converted into a bool, because the value from this function, as well as the self.default, will be converted. So we can only ever return a bool out of this, and now the type system knows. So yes, this is perhaps a much more complicated example than I would normally give, but I did want to show the sheer power of generics and just what you can do with them, and that you can manipulate the type system, especially using overloads, just by setting what the function signature expects. And it's just a little bit of magic that you now know how to do. Let me know in the comments what you plan to use generics for now that you know about them. If you want to know more about typing in Python, then I have a series called Python Typed that you can go and look at. If you want to know other ways that you can make Python awesome, I have a series called Python is Awesome that you can look at. I'll leave both in the end cards so you can choose which one you want to go to next. And I'll see you in the next video for whatever we do next.